pick beta, would be what are we trying to accomplish with this nature reserve? Is this just going to be, a place that species run free? Is it a place that we're going to sort of really intensively manage to make sure that we can either boost alpha diversity or boost beta diversity? And what are our goals? Are we trying to boost things over the short term, boost things in the long term? Ultimately, your goals are going to help sort of shape whether or not you're going to go with alpha or beta diversity. Another thing that comes to mind: we're looking at a bunch of common species, or are we looking at a number of rare species that we might be able to detect? So as different questions which sort of are unasked in this particular thing come into play, so the balance of alpha or beta might make more sense. So you guys said, okay, so beta diversity, and what's the rationale?
Well, we're thinking that there's a bunch of different areas like forests, wetlands, and grasslands that if you boosted beta diversity, you would have more change in species due to their would be a big difference.
Okay, so the idea here is by boosting beta diversity, we make sure that we're sort of maximizing differences in the communities we find in a grassland, which are different species than you'd find over in a wetland, which are different species than you find in a forest. And so by basically making sure that we had lots of wetland, making sure we had lots of grassland and lots of forest, all in our 5,000 acres, we could sort of maximize beta diversity so that each of these habitats would be complementary to each other. All right, that's one approach. Team Alpha. Yes?
I think that since you have so many different types of places that you're already going to have a pretty maximum beta diversity because different species live in different climates. So instead of focusing on the differences of species, focus on increasing the amount of species of each of those, and you'll naturally get a high beta diversity.
Well, you might or might not get a high beta diversity. So for example, we could manage the grasslands really intensively for the highest alpha. And the highest alpha might not include the grasshopper sparrow or Henslow sparrow or bobolink or other of those sort of these rare grassland birds that tend to disappear under conditions of very high diversity. So, when you go to the forest and sort of do the same thing, it sort of maximize a lot of forest edge, early successional forest and late successional forest, and end up with a lot of weedy species, which would give you the highest alpha diversity in the forest. But it might come at the expense of really cool birds like scarlet tanagers or cerulean warblers. So it's not just that high alpha diversity is going to lead automatically to high beta. So, and again, really sort of thinking about how these scales come into play is hard as you try to think through it, which is sort of why we're doing this. It seems really clear when it's like alpha, gamma, beta, but when you sort of start thinking through the implications of it, it gets a little bit muddy. Other team alphas. No. Other team betas. Yes?
Would you think I should run it on the board?
Sure.
Okay, so the idea is it combines a lot of different things about how diversity is strength and how disturbances can affect an area. So let's say it's maybe a disaster.
Tornado.
Fire, okay. A terrible thing to happen. That's our game. Okay, so you have the forests, and you have the grasslands, and you have a wetland. And your disaster affects everything. This marker sucks.
They all suck.
Wow.
Okay. One over here that's
Thank you for your service. That's wonderful. Okay, so this hits the area. And so if we talk about alpha diversity, there's species here, species here, species species one. This is one species right here, this is one species right here, and this is one species right here. So all these different species is like relatively homogeneous across the entire area. But say that same disaster strikes a place where I spent all my money doing beta diversity instead. So there's like one species here, and then like triangles here, and then there's a square here, there's a circle here, and then there's a Rhombus. Thank you. A rhombus. Give it some representation. Okay. And then there's a squiggle, which is probably the snake. And then there's a. I'm not doing that. Okay. And then a cube. There's a cube species because nature's like that. Okay. So then the disaster hits the area. And the star species, they don't like that. Bi-star species. But then this one over here, this one thrives. These over here thrive. These over here thrive. But then the disaster, it's really, really bad to the squigglies, right? And let's say squigglies are a keystone species. Bye-bye. There goes all the diversity in the area. But then I improve beta diversity over here. So the disturbance in the entire area actually thrives a lot more as a result.
Ladies and gentlemen, I'm done with this semester.
Your model,
You have to answer questions now. So.
yeah, your model assumes that the alpha diversity we're talking about is over the entire range and not necessarily for grasslands it's separating out grasslands, forests, and above.
That's true.
What if we try to maximize alpha for each? That doesn't do. Well, let's see how we have.
Well, my scenario is more contemporary. So, for instance, like climate change, it affects all array of like life and everything. Like, no one's gonna like it if heat increases or like climate change actually like changes the climate entirely. So, yes, alpha diversity will be good in some cases because that's what a community sustains itself on. But then beta is going to allow us to achieve more diversity across a really large region in terms of climate change. Or like, who said fire? Was it you? It was you. It was a person. What was your question?
So what if you have, so as Professor Mooney was saying, it depends on the area you're looking at.
Okay.
What if the area is highly resilient to disturbance anyways? What if looking at this as the fact that disturbance in particular would be kind of pointless to either side of the argument if the area we're looking at is already highly resilient?
I'm typing. What are you typing?
I love knowledge, but I don't have it quite yet. So, okay.
What the
Give me
f-
questions. I can't.
So if the area is already highly resilient to disturbance, okay, what we're looking at, then wouldn't this argument led to either side of the debate because the areas wouldn't really be that bad of a disturbance? And again, what kind of factors we're looking at here?
Again, the scenario is to one specific case, though. And everything. I'm saying that beta diversity is allowing all these species in the area to diverge and give all these different species. And then tying with our last lesson and last test and everything, more diversity leads to more community health and everything, and more survival for all species entirely.
So you presumably narrow it down to one specific environment, one specific case,
One scenario,
instead of the
yeah.
broad scenario of the question
You
actually.
give it a broad scenario in the first place, and I decided to put specifically my scenario in the first place. Yeah.
Okay, so as a result of your disaster, this one species was wiped out and was devastated. But in order to get it back, wouldn't you have to increase alpha diversity to help those dwindling numbers? I mean, most conservation things right now, like polar bears and elephants, they focus on one species, bringing one species back and helping it.
So at one point, I had one problem, and needs beta diversity to tackle that problem. Let's say I get funding again because, you know, I'm lucky or something, or I'm rich. So now that that problem's actually hit the area, now I can focus on alpha diversity after I first concentrate on beta diversity, as compared to I only focus on alpha diversity before, and my community was hit a lot harder because I decided to focus on that diversity rather than the other kind of diversity.
Because most conservation effects are as a result of a disaster or something. Like, we're just trying to clean up the problem, we're not trying to, like, you can never predict what's gonna happen.
Every day. I know.
Alright, I'm gonna go ahead and get my seat now.
Okay.
That's awesome.
So, excellent points all around. I appreciate the break. But on the topic of conservation, which we get to towards the end of the student text that we're reading for today, one of the key strategies that's really important for conservation is to not focus on one exact strategy. So for example, in the real world, there's not just one 5,000 acre nature reserve, it's not yet, right? And because there are multiple ones, it makes sense that perhaps in some of those, we would emphasize alpha diversity. In other ones, we would emphasize beta diversity. because any one plan can't possibly handle all possible contingencies. It can't handle the fire, right? Or the disease that comes through, and like West Nile that sort of wipes out your crows and your blue jays and your other corvids. So because there's not one strategy that sort of fits all, effective conservation doesn't focus on just one strategy in all places at all times. There might be organizations that have sort of one strategy as what they do. Perhaps you might give money to such an organization. However, it's important to recognize that one strategy just doesn't work in all cases. So, alpha diversity, beta diversity, it depends. You can make good cases for both possibilities, and depending on how the future plays out, alpha might have been the right choice in retrospect, or beta might have been the right choice in retrospect, but we don't know. So for that reason, sort of both strategies are good. Complicated, but important. Any questions on alpha and beta and gamma diversity? And what I'd like to do is shift into the topic of island biogeography. Very cool topic. So, ecologists have studied islands for decades, actually centuries. If you go back to the 19th century, there's a lot of interest in the islands, whether they were Galapagos, Canaries, or the Western Antilles. Islands are great for research because they are fundamentally simpler systems than trying to do research on continents. They're smaller. Get an island small enough, and you can exhaustively survey every plant species present. You don't have to do on a continent. While on a 30-acre island, they're much more numerous than continents. If you're trying to do biogeography research on continents, we've got 7. One of them is basically ice cover. However, millions upon millions upon millions of islands all over the world. So there's opportunity for replication. We basically create ideal microcolonies because we have islands of different sizes, different shapes, different degrees of isolation. So there's all kinds of ways we can sort of not experimentally manipulate things, but as experimenters, control for things like island size, or control for things like how far apart islands are from each other, or control for things like, are they sort of long and skinny, or are they sort of big and round? So very ideal for studying biogeography. The theory of island biogeography is really sort of predicated on 3 key patterns. And the first of those patterns is the relationship between area of an island and the number of species we find there. Here we have data that's represented in logarithmic scales. So for our area of our islands, we go 10 square kilometers, 100, 1,000, 10,000, 100,000 square kilometers. Numbers of species, 10, 100, 1,000. So if we did not transform our data and had a linear plot, it would sort of go up in asymptote. However, on a logarithmic plot, we get sort of these nice relationships, this nice straight line. So the general idea is that big islands, they have more species than small islands. And it's not just chance that they have, but there's actually a nice underlying relationship, nice mathematical relationship that sort of relates size to species abundance. That formula for this is called the species area relationship, and it was first worked out in the 1800s. But essentially, if we look at the number of species on an island, it's a function of the area to a scaling constant and a linear constant. If we could rewrite it in logarithmic terms, then log base 10 of the number of species you find on the island is the logarithm of some constant c plus the slope z multiplied by the log of the area. So that is the mathematical relationship between a straight line. Z is a value that depends a little bit, but it's around 0.25. I'm trying to think I'd ask you, but there's a pretty constant slope on it. All right, so species area relationship, bigger islands and smaller species, have more species than smaller islands. The second sort of element of the theory is looking at the relationship between species richness on an island and the degree of isolation of that island. So here, the thinking is single isolated islands are going to have fewer species than islands that are not isolated, even if you hold the size of that island constant. Island size is constant. If they're more isolated, they're going to have fewer species. So here we have a number of islands in the beginning, and then a number of isolated islands at greater distances. And we see that for a given area, these more isolated islands are going to have 5, 9, 10 species compared to a less isolated area, which might have 25 species. So isolation can further reduce the number of species you find on a given island. The third element, it's the third and final element of pure island biogeography. It's an idea called turnover, or the change in species composition of location through time. And I'm going to tell you briefly about one of my favorite volcanoes, Krakatoa. This was the most massive volcanic eruption in modern times. This eruption took place in 1883. And this island is located in Indonesia. The volcanic blast could be heard at distances of 3,000 miles. Okay, so again, it's enormous. The entire island was basically destroyed. And basically exploded, blown apart. There was a small part that began to rise out of the ocean known as Mount Krakatoa, or child of Krakatoa, which you can see here. And what happened was, it was a catastrophic, obliterating event. Nothing survived the blast of that island. However, over time, vegetation began to return to the island. These are actually pictures of Krakatoa now. You see parts that are sort of still barren, other parts have vegetation. And even though this island was utterly destroyed in 1883, there were some studies that took place in the early 1900s looking at bird species on the island. So by 1908, there were 1908, there were 13 species on the island. By 1921, this had risen to 21 species. But between 1908 and 1921, there were 20 colonization events, new species arriving on the island from surrounding islands. And 2 of the birds present in 1908 had gone extinct. Not extinct in the grand general scheme, it's just extinct on that particular island, a local extinction. And then if we play it forward, by 1934, there were 34 species on the island. And during that time, there were 4 colonization events, 5 extinction events. So we had this process of new species arriving, other species sort of dropping out. And today there are 32 species of birds on this island. Okay, so roughly what was there in 1934. But many of the birds present in 1934 were no longer present now. This whole process of turnover suggesting that the community of birds on Krakatoa is actually fairly dynamic and changing. So we're going to put these three pieces together: the species-area relationship, an isolation relationship, and a dynamic of turnover. So the number of species you're going to find on any particular island. And we're going to look. This is sort of a weird graph. If you ever ask me about this graph, just call it the saggy X. If you ask me about the saggy X, I will know exactly what you're talking about. So what we have on the x-axis here is the number of species present on our island. It ranges from 0 all the way up to P. P is the number of species you would find on the mainland area of a similar size. The y-axis is kind of weird. This is just rate. You can think of it as number of species colonizing per year, number of species going extinct on the island per year. And so what these lines represent is sort of this first line rises, it's very high and basically drops as species richness increases, is the immigration rate to the island. So if you think of a situation where there's no species present on an island, there's lots and lots of opportunities for vacant niches for species to come in and establish. So the number of successful immigrants to that island is initially going to be very high, no competition. But as species arrive and establish, they basically provide sort of a competition counterbalance for additional species coming in. So additional species can continue to colonize, but at a slower rate. As species as they become more abundant on the island, the rate of successful colonizations gets lower and lower. Let's look at the reverse side. All right, what's the extinction rate on an island with no species? 0, right? And initially, because there's very little competition, the likelihood of a population going extinct on that island, should it colonize, is going to be very low. There's no competitors. But as additional competitors arrive, that extinction rate is going to rise and rise and rise until once there's lots and lots of species on the island, the extinction rate in any given population is extremely high. So what this theory suggests is that there's fundamentally a balance between immigration rate and extinction rate, such that when the immigration rate is equal to the extinction rate on an island, so those rates are equal, that is going to give you the number of species you can predict to find on an island. So the sagging X diagram fundamentally tells us the number of species you find on an island is going to be a function of the extinction and colonization rates, or immigration rates. And when those two rates are equal, the island is in equilibrium. Yes?
So like what happens when a species immigrates in and it causes the extinction of other species? Like we learned about the honeysuckle and everything like that. Is that kind of rare? Or?
It's not common, but it happens. And typically what we see is a decline in species, but that sort of creates new opportunities for additional species to come. And as basically those areas will return to some sort of equilibrium as you have opportunities for new colonies. It might not be every year, every decade, but as species go extinct, that creates opportunities for available space for new species to come in. It's not to undermine arguments for conservation at all.
Yeah.
All right, but over longer term, there's this equilibrium on these islands. So this is the complicated version of the saggy X, but it's really not that complicated. What we've done here is we've added information about island size and island isolation. So thinking of immigration rates, again, we know it starts off high, and as the number of species become more common on the island, the immigration rates sort of drop down. And what we have here is a comparison of an island that's relatively close to the mainland, one that is not really isolated, versus an island that's much more isolated. So these isolated islands have basically lower immigration rates because of their isolation. That is, because they're, by definition, isolated, the number of immigration events they would receive per given year is less, just due to chance due to isolation. You'd expect for an island relatively close to a mainland area that might get regular migrants. So the general idea is near and far, continue to drop just as normal. And if we were just to sort of focus on one line here, one station line, for a small island, the number of species that we'd expect to find in equilibrium on an island of equal size is going to be lower for an island that is isolated than an island that's closer to the mainland. That equilibrium point, the more isolated the island is, the further that's going to shift to lower species at equilibrium. Flip it around a little bit and look at just look at near islands, but look at the consequences of island size, small versus large islands. Small islands have less area, so less space to pack in more species. And so as a result, the extinction rate rises more quickly than you see on a large island, where the rise in the extinction rate is more gradual. So for a single island for a single immigration rate for two islands equally distant to a mainland, a small island is going to have fewer species in equilibrium than a larger island. So this diagram is basically looking at the consequences of isolation and the consequences of island size, and showing how the number of species we expect to find in equilibrium could be very low for a small isolated island, to a bit higher for a large island that's isolated, to a bit higher for a small island close to the mainland, to a bit higher for a large island. All very well and good. This was actually experimentally tested. Your book mentions this briefly, but it's almost too surreal to believe. This was tested about 1970, where the experimental design was they were going to use these mangrove islands and basically build up scaffolding, put a tent over them, and drop in some really potent pesticides to kill off all the insects, remove the tent, and then sort of watch species as they recolonize these mangrove islands. And what we have is we have distant mangrove islands. These are sort of number of species over here on the y-axis, and the number of days, so time on the x. Distant islands sort of rose up and dropped down, as you would sort of predict. Islands relatively close to the mainland of equal size, much higher species richness as you would expect. So it's been experimentally tested in a very sort of extreme, convoluted way. And I think to wrap up today, I'm going to leave you with the amazing, I mean, this song, you're going to love this song. My song just dropped. This song. This is going to be the summary of the equilibrium theory by biogeography.
was great, but there was debate, so Simbalom stepped up to the plate to find out if communities really formed in this way. Found themselves some mangrove stands and spread them with a human can. Create denuded island that vary in size and space. The crowd just came back and shuffled